Okay, so before we start, I have to give a special thanks to the authors of this paper. Without them, my final project would not be possible. In particular, big thanks to Carleen Markey, I hope I'm pronouncing that right, for answering my questions on Twitter. It was a big help. Let's establish the main goal of this research. From the name, we can see the cluster assembly part and the origin of mass segregation. These are the two main aspects of this research. The first part, cluster assembly, is examining and simulating the evolution of a molecular cloud, in particular, the star forming and clustering aspect of it. The second part, the origin of mass segregation, is to closely track the clustering of these individual stars of different masses for mass segregation and check whether or not mass segregation is primordial. We'll talk about that in a bit. Now let's move on to talk about clusters and mass segregation. A cluster is defined as a neighborhood of stars that have more than a certain number of stars within a set radius. The mass segregation, on the other hand, is defined as the process of which heavier objects in a gravitationally bound system move towards the center. Now, these two terms in astronomy do not have a consensus definition, so the researchers had to make up their own. For clusters, they use the definition from DBSCAN. So any star above the H burning limit, the hydrogen burning limit, whose certain number of closest neighbors are within a certain distance is considered a core particle. And these core particles and any particles within this certain distance are considered to be part of the same cluster. Now, for mass segregation, strictly speaking, it is the process of heavier objects moving towards the center. That is the strict definition. For this project, mass segregation is defined as anything regarding heavier and lighter particles moving in different ways. Okay, so let's talk about this simulation. Now, this is the judicial simulation, or the first simulation. And as you can see, the original molecular cloud, which is right over here, was a sphere. Now, as time goes on, the units are in million years, you'll see that stars begin to form at different sites. In particular, let's look at the 5 million year mark. The 5 million year mark, I've marked it over here with this red line. And this graph may seem a bit convoluted at first, but let me explain. So, if you look at this graph over here, you'll see that there are multiple different star-forming sites. And there's this one site that seems to be very large. This cluster that seems to be very large and has a number of small clusters within it. Now these are called subclusters, which from before, as you can see, are small clusters within a larger cluster or a larger structure. Now, the thickness of the lines in this diagram indicate the total mass of these clusters. As you can see, this red line is particularly thick, and this references to this larger cluster over here. And there are a lot of clusters, and this also references to all these clusters over here. Now, as you can see, as time goes on, the clusters form a gigantic dominant cluster in the center, and this is consistent throughout the simulation. From the 7 million year mark, which is right around here, you'll see that clusters begin to split up. This is because of gas expulsion, and gas expulsion is where the newborn stars start to expel gas out from the cluster, terminating the further star formation. Now at the 8 million year mark, as you can see from right over here, all the clusters are spread out. They're unbounded. And from this picture over here, you can see that all the stars don't have like a dominant cluster in the center as in the 6 million year mark. Now, this simulation was the first simulation, the building block. We changed, or rather the researchers changed, different initial conditions of the simulation process, so these parameters. I'll just go over the basics. So turbulent driving. Turbulent driving is where you add turbulence to the molecular cloud, a constant turbulence flow to the molecular cloud. As you may expect, this slows down the clustering process significantly. And also, we changed the shape of the cloud. So we changed the shape from a sphere to a box, a cubic box with the same volume. Now, since the box-shaped cloud has a weaker gravitational pull, the clustering process is also slowed down. We also changed the initial velocity dispersion, or the initial turbulence, and the surface density. Now, the changes in velocity dispersion do not change the large structure. So this structure from 6 million years, this doesn't really change. There's still a dominant cluster in the center. However, the changes in surface density does affect star formation efficiency. What this means is that if surface density is too low, well, stars fail to form. And if we decrease it by a factor of 10, you'll find that less than 20 stars form in the simulation, which is not enough to do clustering analysis. But except for these extreme cases, the changes in surface density still do not change or affect the overall structure of this central dominant cluster. So, what do we know from all of this? Well, first of all, for the first simulation, the clusters form in several sites within the giant molecular cloud, each with very strict mass segregation. So as you can see from right here, each cluster or each individual subcluster is very, very strictly mass segregated, which means that the heavier stars in blue are at the center. However, if you look at the cluster as a whole, the blue stars are not centralized, so it is not strictly mass segregated. But with the definition from this project's researchers, we can find that, well, the giant cluster is still mass segregated. It was mass segregated from the very beginning because, as you remember, the mass segregation definition is where the heavier stars and the lighter stars move in different ways, and it is very obvious from this diagram that they do. Now, the second thing that we learned is that turbulent driving and the shape of the cloud changes the overall structure of the star formations. The third thing and the final thing that we learned is that changing the initial turbulence and also the initial surface density does affect star formation efficiency and the history of the star formation, but it does not change the large-scale structure, so this dominant cluster in the middle right here. And all in all, this was a very fun project to work on.